Hello, my name is Alexis Anagnostakis. I am a PhD student at the University of Lorraine under the supervision of Antoine Leger and Denis Villemonet. First of all, I'd like to thank the German Probability and Statistics Days for this opportunity to talk about my work, which revolves around the local time of sticky diffusions. In particular, what we want to do is to approximate the local time of sticky diffusions. But before going into further details, we will explain what are sticky diffusions and what is the local time, so we know what we're doing. So before stating what is a sticky diffusion, let's see what is a diffusion process. A diffusion process is a process that satisfies a strong macro property and its trajectories admit almost surely a continuous version. So the macro property, what it is, it means that in order to make predictions about the future of a process, knowing the past and the present is just like knowing the present. So so it means that the present state synthesizes all the information about the past of the process. And we also are in one dimension, and in one dimension, one thing we can do is to characterize a diffusion process with a pair composed of one function and one measure. The function is called scale function, and what it does, it tells us in which direction the process has more probability to move. As we're in one dimension, this direction is up or down. M is a measure called speed measure and tells us at which speed the process exits compact intervals. The higher the speed measure, the more time the process takes to exit compact intervals. Now, okay with diffusions, but what are sticky diffusions? Sticky diffusions are diffusion processes that spend a positive amount of time around a certain point, which this point we will suppose it will be located at zero for sake of convenience. And also the time it spends at zero will be random also, because if it is not random, it defies in one dimension the strong macro property. And not only also the weak macro property. Anyway, the reason why I introduced diffusion processes using the scale function speed measure is that this particularly adapt for sticky diffusion. Our sticky diffusions are diffusion processes that have an atom in their speed measure, and the weight of this atom is called stickiness parameter of these processes, and the higher the stickiness parameter is, the more time the process will spend there. The most elementary sticky diffusion process is the sticky Brownian motion, which is a process that behaves exactly like a Brownian motion outside of zero, away from zero, and it has here a sticky point at zero with weight rho. And we can see that this is a scale function, and the rest part is the speed measure of a standard Brownian motion. This is a trajectory, a simulated trajectory of the sticky Brownian motion using an algorithm we devised in a previous work called STMCA algorithm. But there are many ways to simulate this kind of process. As we can see here, away from zero, it behaves like a standard Brownian motion, and we see that every time it touches zero, it spends a positive amount of time there, which is random. So, okay, with sticky diffusions, let's see now what is the local time and how to approximate it. So the local time is defined for any semi-martingale process, and it is another process which is increasing. It actually increases only when we are at zero. With this alternative formulation, you can see this pretty clearly. And we can define it as the term that compensates this equation. So this is the local time. And thanks to Ito Tanaka formula, we can alternatively write it as a following limiting probability. And this is actually, this formulation, we'll use it to approximate the local time, as we will see later. But as we saw, the local time is defined for semi-martingales. So the diffusion process we want to approximate the local time must be semi-martingales. This is why, and for other reasons, we study sticky SDs, which, like the sticky Brownian motion, are diffusion processes that behaves like a standard SD away from 0 and have a sticky point at 0. One way to see that is using, again, the scale function speed measure characterization. We see that this is the scale function of the non-sticky version of the SDE, and this is the speed measure of the non-sticky version of this SDE, of this SDE. And this is the sticky point at 0. So this process has semi-martingales, and not only there are semi-martingales, thus the local time exists. The local time also plays a crucial role in describing their trajectorial behavior. As we can see right here, we can express a sticky SDE as a solution of this system right here. And this system, this is the behavior of a process away from 0, and this is what happens at 0. And we see that the occupation time at 0, which is how much time the process spent at 0, we also denote this with a, let me write this properly. Oh, sorry. A T 0x, this is the occupation time at 0, is actually proportional to the local time. And also we can write this thing, which will be important later. If we divide the occupation time by the local time, modulo a 2 or a half, we get the stickiness parameter. Now, how we approximate this local time? So let's take the most elementary sticky diffusion process, which is a sticky Brownian motion. We write its local time as a limiting probability, as we saw before. The quadratic variation of the sticky Brownian motion is this thing right here. And we would like, so I remove the ds here. I'd like to approximate this integral, this with a Riemann sum. So, and if we do this, we have this double limit. So in order to approximate the local time with this kind of thing, we need to answer two questions. The first thing is this thing Riemann integrable? So we can write it like a sum right here. And the second question is, does the double, in which conditions, for what is the relation between epsilon and ni, such that this double limit converges and converges to a thing that we wanted to converge. So the second question for Riemann integrability, we can answer it. It is Riemann integrable, in fact. I won't prove it, but it is, believe me. Actually, we also proved something stronger, but I'm gonna go back into this later. And the double limit question is our results, actually. In fact, in the case of non-sticky SDEs, Jacob proved a theorem that tells us what happens. And what happens is that if epsilon equals n to the power minus a, for a between 0 and 1, then the aforementioned thing converges to the local time, actually. Actually, it's a more general result. We take a test function g, and if it's band integrable, and we have this condition alpha, we have this convergence to the local time. And what we've managed to prove so far is that for a sticky Brownian motion, we have this result. So we take alpha between 1.5, 0.5. So it's a more constrained case than the hypothesis of Jacob. Actually, I strongly believe that we can prove it for until 1, but I have not done this so far. And the other condition that we must have, and it's mandatory, is that G0 must equal 0. And the reason why we must absolutely have this is that if G0 is not equal to 0, then we'll have a number of terms that is of order n, and this is from what we said before about that the time the process spent at 0 is positive and is random. This thing will simplify with this, and we have a G0 here. So we have G0 times n to the power of a, which will go to infinity. So this thing will diverge if G0 is not equal to 0. But to contrast this with Jacob's results over here, is you can take also here G0 equals 0. it won't change anything because we only see the integral here. So actually, you should have the same conditions actually for two things to converge. Anyway, in fact, we don't prove this result. We prove something more general. We prove a rescaled version of this, and the rescaled version of this, along with the trajectorial behavior of a sticky SD, which implies Girsanov, result in extending the result for a sticky Brownian motion to the result for any sticky SD. So if we have X a solution of a sticky SD, G a test function so that G0 equals 0 and an alpha, so far we've proven for between 0 and a half, we have that this quantity over here converges to the local time. That's great. Now, what can we do with this answer? We can use it to estimate the stickiness parameter of a diffusion process, which is it's something very important. So you have a sticky process, you have a stickiness parameter. One natural question is how much is the stickiness parameter if we observe a process? So we have here a ratio. This thing we've proven, it's not very hard to prove it. It converges to the, it's not trivial, but it's not too hard. It converges to the occupation time at 0. And this thing we've proven that converges to the local time at 0. And as we saw before, if you divide the occupation time by the local time, it gives us a stickiness parameter. So this thing is a consistent estimator of the stickiness parameter. But we must be careful, because if a process does not hit 0, then this thing will equal 0. This thing will, I think it will equal 0. So it's 0 divided by 0. So it's we don't know what it is. It's not defined. So in order for this estimator to have some sense and to be consistent anyway, the process must hit 0. And one condition we can impose for it to hit 0, it is if we are on the event, on this event right here, which means that the local time is positive. And in order for it to be positive, you must have hit 0. On this event, this estimator is consistent. And this is natural because how can you assess a diffusion process that it's described by a scale function speed measure that are local in character? How can you assess the stickiness of one point if you never visit this point? That's so it does not make any sense to try to estimate something that you're not even observing. No, so what we'd like to do right now is, first of all, I've written second actually, what happens for alpha between ½ and 1. That's one thing I'm working on right now. And the other thing that is more fundamental, more interesting from an application point of view, is to find the speed at which this estimator converges to the stickiness parameter, because if we know the speed, we also can devise a central limit theorem, create Neumann-Pearson tests, and for example, you have a trajectory of a diffusion process. You want to know if it's sticky at one point. Well, you run the Neumann-Pearson test, and you can assess the stickiness of that point, having the observation. Okay. So that's it. Thank you very much for your attention. This is a link to the article we would like to publish, and I hope it will be available soon on the internet. And have a nice day. Thank you very much.